in the previous lecture, I talked about some of the problems for finite state machine, where we have converted a language into the finite state machine. Now, in this video, I will talk about two topics. One is some few more problems from finite state machine, and then I will talk about non-determinism concept. Okay, so let's start with some more problem with the finite state machine. Let us say the language L is defined like this. It is containing of all the string W. W is belonging to 0, 1 star, and W starts with 0, 1, 0. Okay, so the property of this particular class of language is starting 3 symbols are nothing but 0. The first symbol should be the 0, the second symbol should be the 1, and the third symbol should be this 0. After that first 3 symbols, what are the other symbols? That doesn't matter. It may be 0, it may be 1, right? So let's start designing the finite state automata for this particular language. Now, first of all, let's think about the state where we are interested. Basically, if we think about the language, as I told you, the first symbol should be the 0. So it might possible that I am not getting any 0, right? So no 0. Now then someone has seen, the machine has seen the 0, the first 0. Then it will see, let's draw it in some nice way. The machine has seen the 0. So first of all, the machine is seeing no 0. That might be the possible. The first bit is obviously not 0. First symbol is not 0. Then the machine has seen a 0. So this is a 0. Then machine has seen a 1. That means already if the machine has seen 0 and then the machine is going to this state, then already the first 2 symbols the machine has seen is 0, 1. Then the last thing the machine is seeing is 0, 1, 0. That is the mean. The first 3 symbol is 0, 0, 1. That is the second first 2 symbol, and this is the first 3 symbol. That is 0, 1, 0. Right? Okay. So now the problem is, it is very required that the first symbol should be 0. So if the first symbol is not 0, if I have not seen any 0, I mean to say if I have not seen any 1 nor I am 0, and if I am seeing a 0, then obviously I will go to this state. But if I see a 1 and the 1 is not permitted to be the first symbol in the string, so I go to the dead state. This is sometimes called the dead state, and you cannot come out of the dead state. So whether you are after getting a 1 as a first symbol, whatever you have seen is not permitted, right? So what is the meaning of this? you can have something like 0, 1, 0, 1. This is permittable, this can be accepted because the first three symbols are 0, 1 and 0. But 1, 0, 1, 0, 1, this is not permittable because the first symbol here is 1 and the first symbol should be 0, right? At the same time, if the first symbol is 0 and the second symbol is again 0, then also it is not acceptable. So this string kind of things are not acceptable because the first, the second symbol should be the 1. So this kind of strings will be accepted, but these kind of strings where the rules are violated should not be accepted. So if we figure out that the rules are violated at this state, then why to worry about other things, right? Why to worry about other part? Because the rules, once the rules is violated, the strings should not be accepted, right? So we go to the dead state, and after that whatever is coming, whether it is 0, 1, that is immaterial once the rule is violated. Now, after the first symbol, if I am getting a 1, then I am in a valid track. But then if I am getting a 0, then also I am violating the rule because the second symbol should be the 1, not be the 0. Now the third symbol, if we talk about, it should be 0, and that's why we will reach to this state 0, 1, 0. But if the third symbol is not 0, if it is 1, then also the rule is violated, and then we come to the dead state. But yes, after there is no restriction, what will come after this third symbol? So whatever is coming after the third symbol, that is immaterial, we should accept it, right? So this is the start state and this is the final state, right? And this is the dead state, okay? So let's see whether the machine is working well. So let's give the input 0, 1, 1, 0. And as we see here, as we are seeing here, that the third symbol is not 0, practically this kind of string should not be accepted. So let's start how the machine is going to reject this. For this I am giving the number A, B, C, D, and why give this state as a D, then it is E, right? Then starting with A, and what is our input? It's time to process the first symbol, that is 0. So we go to the state B. Then need to process this 1. So we come and process 1 and going to the state C. Up to this point we are going in a very valid direction. But if we go and process this third symbol, that is 1, we go to the state D. And after that we are going to process this 0. It is, the machine is in state D. There is no more symbol to process. So what is the final last state? It is D. And since D is non-final state, so 0, 1, 1, 0 is rejected. Okay, so this is how I am or the machine is rejecting this particular string. Let us see whether the machine is accepting something or not. 0, 1, 0, 1, 1. And what we are observing here, the first symbol is 0, the second symbol is 1, third symbol is 0. After that there is no restriction. So this should be accepted by the machine. So let's see how the machine is accepting it. A, that is the start state, and it's time to process this first 0, right? So we go to the state B, then time to process the second 1, and it is going to the state C, then processing this third 0 and going to the state E, then processing this 1 E, and finally processing this 1 going to the state E. So after processing the final 1, there is no more symbol to process. So what is the last state? The last state is E, and E is a final state. E is a final state. That is why 0, 1, 0, 1, 1 is accepted. Right? 0, 1, 0, 1, 1 is accepted. Right? So this is how the machine is working. Let's discuss about one more language. The language is L, containing of all the strings W, where W is belonging to 0, 1 star, such that W contains 1, 0, 1, 1. So W is containing 1, 0, 1, 1, right? So the language is saying somewhere in the string, I am not specifying whether it is on start, whether it is on middle, or whether it is on end portion, but somewhere in the string, if there is 1, 0, 1, 1, then we should accept, and if there is no where in the string we find 1, 0, 1, 1, then we should reject it. So let's see how it will be designed. First of all, as usual, since we are interested in 1, so if we are getting 1, then it is a chance to build up 1, 0, 1, 1. But if we are not getting any 1, then there is no chance of building 1, 0, 1, 1. So there is no 1, right? Then the state here, it is representing 1. Then the valid string should be 1, 0 to build up 1, 0, 1, 1. Then 1, 0, 1, and finally 1, 0, 1, 1. And if we find 1, 0, 1, 1, and after that we are getting anything, that is immaterial. Only things matter is whether the string is containing 1, 0, 1, 1 or not, right? Somewhere before 1, 0, 1, 1 we can say this is this, you can say no 1, or sometimes you can say before 1, 0, 1, 1. That might be one logic, right? So something you have seen before 1, 0, 1, 1, then you are getting a 1, then it is a chance to build up 1, 0, then it is a chance to build up 1, 0, 1, and finally there is a chance to build up 1, 0, 1, 1, right? And after this 1, 0, 1, 1, whatever we are getting, that is immaterial, right? So let's think, if we have found 1, 0, 1, 1, that means we should accept, right? So this should be the accepting state. And something before 1, 0, 1, 1, that should be the start state. Okay? Now, if we are here, that means we have not seen, the machine has not seen any 1, and if the machine is getting 0, that means still the machine has not seen any 1. So if the machine is getting 0, it will here, right? But this means that machine still has not seen any 1. If the machine has seen 1, and then it is saying 0, that's a different case. But machine still has not seen any kind of 1, it is only getting 0, so it is coming back to this state. Now, if the machine has seen 1, it will go to this state. Then the machine has seen 0, then only the machine will come to the state. Here, from this state, if the machine has seen 1, then it comes to this state. And finally here, if the machine has seen 1, then it will come to 1011. And then having 1011, then that means the machine has already seen 1011, it will accept. That means after this, if I am getting anything 0 or 1, that doesn't matter. So having the 0 or 1, it will come to the same state. Now final state. Now think from this case. What if I am getting a 1? By getting a 0, I have already seen 1, 0. But by getting a 1, right? So I have seen a first one, suppose the machine has seen a first one, then the machine is seeing consecutive ones. Okay? If the machine is seeing consecutive ones, that means there is a chance again from last one, there is a chance that machine will see 1011, right? So even though machine has seen multiple 1, but still there is a chance that from the last one it can build 1011, right? So the machine will return to the same state. Okay? Because machine has already seen a 1, means machine is not losing the 1, right? Then from this state, what if I get a 0? Now let's analyze. I have already seen 1, 0. Somewhere I have already seen 1, 0. And we are seeing, it is required to get a 1, 0, 1, 1. After the 0, it is required to get a 1 to build up the entire string, means to build up the 1, 0, 1, 1. But if we are seeing a 0, okay, then the actual pattern, that is 1, 0, 1, 1, must lost. So we need to rethink and we need to reprocess. So we will come back from the start and we say we have not seen anything yet useful, right? And whatever we have seen useful, that is lost, right? So we need to process from the start. Now come to this state. Here you have claimed, or the machine is claiming, that it is seen 101. But if the machine is saying 1010, right? 1010. In this case, what will happen? The machine, even though the machine is losing the pattern, but the machine is not losing the pattern completely. Still, there is 10, right? Still there is 10. So there is a hope that if I get 1 later, then we accept it, right? So the machine will not come to the start state to process everything from the start. Rather, the machine come back to this state because the machine has already seen 10, right? It is not losing the pattern completely, right? So this is what the finite state machine for this language L. Okay. So let us see whether this particular machine is accepting something or not. So let's take an example. 1 0 0 1. Let's take this 1 0 0 1 0 1 1 0. Whether this particular string is accepted or not. By simply analyzing this string, we can say there is a pattern 1 0 1 1 here. Okay, and if we have seen this pattern, we should accept. That means the machine should accept, right? So let's see how the machine is accepting it. Okay, so let's see that. So let's give the number A, B, naming of these states, C, D, and E. So we are here, A is here and we need to process this one. So I am processing this one here and going to the state B. Then from the state B, I am getting a 0, right? From the state B, I am getting the 0 going to the state C. Then by getting this 0, I lost the pattern completely. So I come back to the state A. Then I got this 1. So I am trying to rebuild the pattern again. There is a possible chance of rebuilding the pattern again. Okay, there is a chance of building the pattern again. So what we will do, this 1 will be going to the state B. By having this 0, then we are going to the state C. By having this 1, we are going to the state D. And by having this final one, we are going to the state E. And then we are processing this final one. This is what? We are going to the state E. And after processing this final one, there is no more symbol to process. So what is the last state? The last state is E. And E is a final state. E is a final state. So accept the string 1 0 0 1 0 1 1 1, right? So we are going to accept it. Okay. Similarly, we can test that some of the strings which is not containing 1 0 1 1 is rejected by this machine. Okay. Now we have talked much about the finite state machine. Let's talk something about categorization of finite state machine, and then we will go for the other kind of machine. So if we have seen the machine, finite state machine, the FSM, the finite state machine, is classified into two broad categories. One is called the DFA. The full form is deterministic finite state machine. The second is NFA, that is non-deterministic a non-deterministic finite state machine. Okay, so finite state machine, sometimes it is called finite autometer. Instead of having the machine, we can say autometer. So here also we can say finite state. Instead of finite state machine, we can say finite autometer. Okay, so both are the same thing, but it is non-deterministic automator or it is deterministic automator, right? Or the deterministic finite state machine or the non-deterministic finite state machine. Now, why these two broad categories are there? This is like a different way of computing the same thing, right? Different way of computing the same thing. So let's see what is the meaning of this different way of computing the same thing. We have analyzed lot of language, and we have analyzed lot of finite state machine. Let us analyze this finite state machine. Here, by having the 0, by having the 1, we come to the state A. Then by having the 0, we come to the state B. Then by having the 0, we come back to the state B. And by having a 1, come back to the state C. And then by having the 1, I come back here and by having a 0 I come back here and then I accept here, right? So let us analyze this kind of machine, what this machine is, and how the machine is computing something. So let us say the input to the machine, this machine is, and obviously this is the starter state. So input to the machine is 1 0 1 0 0. Let us say analyze this input. So how we will analyze? Let's say we are starting with the state A, because A is the start state, we should start from that. Now by processing this one, if we are processing this one, what will happen? If you look out this machine, the machine has no doubt that by processing this A from the start state A, it will again come back to this A, right? There is no confusing in this in determining the next state. Again, if we look at this machine and we need to process this 0, then again the machine has no confusion that when it is in the state A getting a symbol 0, it will go to the state B. Then again, if there is a 1 from B, then again there is no confusion, then the machine will go to the state C. Then the machine will process 0 from C, it will in the state C. Again there is no confusion, and then if it is final 0, the machine is going to the state C. So if we look at the computation or the way the machine is determining result about this input, then we feel that it follows a line, right? If it is following a line, then it is kind of deterministic machine, right? So what we can say, there is two characteristics of deterministic machine. First, no confusion in determining the next state. Every time, not in a single time, but every time there should be no confusion that what should be the next state if I am getting this input. That is one point. And the whole computation on an input, whole computation on an input follows or aligned in a line. Okay, so the computation, whatever the computation done by this machine to get the result for this particular input, obviously follow a line. Why it is following a line? If we find out the basic characteristic by which we can predict this whole thing is, if you look at this state. Now first of all we need to think one point. The machine is only processing two symbols, 0 and 1. So we can say the alphabet for this machine is 0 and 1, right? The alphabet for this particular machine is 0 and 1, because the machine is only processing 0 and 1, right? Now if we analyze any state, let's say we are analyzing the state B, right? So if we think about the state B, how many outgoing branches are there? The first branch is for this 1, so first branch is going for 1, and the second branch is going for the B, second branch is going for the 0, right? So if we look at the C, if you again analyze C state, there is one branch for 0, outgoing branch, and another outgoing branch is for 1. So that means from every state there are 2 outgoing branch, and this 2 is coming from the number of symbol in the alphabet. And another thing, every single branch is for every single symbol from the alphabet, right? So how many branch we expect from A? 2. 1 for 1, 1 for 0. How many branch we are expecting from B? 2. Outgoing branch. I am not talking about the incoming branch, right? So how many outgoing branch we are predicting from, expecting from B? It is 1 for 1, 1 for 0. There is no branch or there are no more than one branch for any particular symbol. That means we are not getting any kind of state. We are not getting any kind of state. Let us say if we are getting this kind of a state is X, and if the outgoing branch, this is for 1, this is for 0, okay, and then there is one more branch for 1, right? If we are getting this kind of state, then there will be some problem, or the computation done by this machine will be different than we have seen. Let us see, let us analyze what will happen. Let us say for 1 we are going to state Y, for 0 we are again going to state Z, and for 1 again we are going to the state Z dash. There are 3 different states, right? And let us say the input is 1, okay? So from X, if we need to process a 1, then there is a confusion. What is the confusion? Where we will go? Whether we will go in the state Y or we will go in the state Z dash. Where we will go, or Z prime, where we are going? There is a confusion, right? So if there is a confusion, then this kind of machine is called non-deterministic machine. So basic idea is, if confusion, then confusion for finding next state, we say it is NFA. Okay? If no confusion at all, what we will say, the next, no confusion at all for next state, then it is DFA, deterministic finite automata, right? So the deterministic finite automata is again a machine which is solving some problem, but the way it is solving the problem is completely different than we have seen in form of deterministic one, right? So what is the main characteristic of non-deterministic finite automata? So if we think about the non-deterministic finite automata, if the sigma is 0 or 1, then there are various possibilities. 1, there is no branch for any symbol. No branch for any symbol. That means whether we will go in which state next, what is the next state is undefined, right? That is one question. There are there are one branch for, or possibly possibly more one or more branches for one input, one symbol. So it might possible there are more branches for 0, but or not for one, I say some symbols, but no branch for other. So that is one possibility. Either we don't have any branch, that also comes under the category of non-deterministic finite automata. But there is another thing, we have one or more branches for some symbols. Say here we have more branches for 0, but no branch for 1. So for 1 we are not finding any branch. In that case it is also comes under the NFA. Third possibility is one or more branch for all symbols. Okay, so for all symbols, whether it is 0 or 1, we may have one or more branches for that particular symbol, right? So if we analyze this thing, what we can say, if let us say this is the automata. Let us analyze this automata, whether this is NFA or DFA. Now if we analyze A, right? So there is one branch for 0, there is only one branch for 1. Okay? If we analyze B, there is one branch for 1, there is one branch for 0. So from both state, and obviously the alphabet is 0, 1, 1. So for both state, the number of branch are 2, that is equal to the length of that particular alphabet, or the number of symbol in the alphabet. So number of branch, so that means number of branch, the number of branches must be equal to the length of the alphabet. Okay, and each branch is for one symbol, right? Each branch is for one symbol, means for this symbol we are not getting any kind of other branch. Okay, so this automaton is kind of DFA, right? But again, if we look at the characteristic of NFA, what we are analyzing, NFA is not saying that there is something missing or there is more than. No, what NFA is saying, there is a possibility of having this thing. If there is no, fine, but if there is yes, then also it is accepted, right? So in this case, from A there is no missing, so no missing, right? From B it is also no missing. That doesn't mean it is completely, it is DFA, that's for sure, but it is also an NFA. It is also an NFA. So basic broad category is NFA. NFA is talking about all the possibilities, right? DFA is not talking about possibility. DFA says there must be this, but NFA is saying there should be some possibility, right? So DFA is basically nothing but the subset of NFA. So what we can say, so if some machine is DFA, so if this machine, if I say M, so if M is DFA, deterministic finite automata, then M must be NFA also, right? But if M is might not be, it might not be DFA. Okay, so if it is NFA, then it might not be a DFA, but if it is DFA, then it certainly be an NFA. Okay, so let us see some examples of NFA, some basic examples of NFA. So examples of NFA, and at the same time we will see how the computation of NFA look like. Means in case of DFA it is following the straight line, but in case of NFA what form it will take. Okay, so let us analyze this NFA. Let us use different color. Okay. So let us analyze this. 0, 1, 0, 1, 0. Okay. A, B, C and D. Okay. If we analyze A, then we will find one branch is for 0, okay, one branch is for 1, and there is one more branch for 0, right? There is one branch for this 0, one branch for this 1, and there is one more branch, this branch is for this 0. So obviously A, and yes, if we talk about sigma, it is 0, 1. Okay, because the machine is again processing 0 and 1, right? So the branch number of outgoing branch from A is obviously not equal to the length of the sigma, right? So if we are having this property, then we can say this machine is NFA. This machine is NFA. So this machine, this, if we represent this M, then the M here is certainly NFA, and it is obviously not a DFA, right? It is violating the rule for DFA. Okay. Again, if you look at the branch B, or the state B, the B is having one branch for 1, but then there is no branch for 0, no branch for 0, right? So again, the rule is violated, and we say it is again the machine is again the NFA. Similarly, we can test out for C and D also. Okay. Now let us see. What if this machine is going to process the input 1, 0, 1, 0, 0, 0. Okay. Now first let us see 0, 1, 0, 1, 1, 0. Not take too long. 1, 0, 0, 1, 0, 1, 0. Let us think about this input. Okay. If this input is given to this machine, then let's think how this machine works and what kind of string it will accept and what kind of string it will reject. Okay. So let's start with A. As usual, we have the start state as A. Time to process this 1. Now if we are here, we think about this, we are here on the state A and we are getting 1, right? So for 1, there is only one branch, right? We return back to the state A, so there is only one branch. Okay, so let's represent it like this: A, and we are processing this 1. There is no more option, there is no confusion that we will come to the state A. Then we need to process this. Then we need to process this 0. So by processing this 0, now the confusion arises. Suddenly the confusion arises. What is the confusion? Where I will go? Whether I am going to the state A again, because by following this route, or we should go to B by following this route. Which route I will follow? So I don't know. That is why I am making this. I need to process this 0. So I can go back to the A, or I can go back to the B state. Both state is valid because there is 2 branches for 0, right? Now then again I need to process this 0, right? So if we are in the state, if the machine decides to reside in the state A, then the machine has again 2 choices. The machine, by processing the 0, machine will go to the state A or the B. Now, if the machine is deciding to stay in the state B, then by processing this 0, there is no branch, right? The machine cannot process 0 because from B it is there is no branch for 0, right? So machine cannot process 0. So machine go and crash. Okay, because the machine cannot process that 0. Okay, but if the machine is crashing, that doesn't mean the computation for the machine is not possible, because again the machine can decide to stay in A or to stay in B, right? Now already the machine has processed this 0, time to process this 1, right? So if the machine is deciding to stay in the state A, there is only one choice. We go with 1, we go with the A. There is no confusion now. Now, if the machine is deciding to process B, stay in B, by processing this 1, the machine go in the state C, and again there is no confusion, right? Now, if the machine is deciding to stay in the state A, then by processing this 0, the machine has again 2 choices. Either it will go here or here. So let me write this here: 1 0 1 0 1 0 1 0, right? So machine has already processed 1 0 0 1 1 0 0 1. So machine is now going to process this 0. So it is machine. If the machine is in a state A and it is processing the 0, the machine has 2 choices. Either it go in this direction or in this direction. So it will stay in A or go to the B. But machine, if the machine had decided to stay in C, by processing this 0, there is no confusion. The machine will go in the state D, right? Now it is time to process this 1. If the machine is already decided to stay in A, there is no confusion. The machine will stay in the state A. But if the machine has already decided to stay in the state B, then by processing this 1, there is no confusion. The machine will go to the state C, right? But if the machine is already decided to stay in the state D, then by processing this 1, the machine go to the crash. Why? Because from D state there is no branch for 0 or for 1 also. So the machine go to the crash. Now if the machine decided to have in state A, and by processing this 0, the machine has 2 choices. Either the machine has the 2 choices here. Either the machine will go in the state A or in the state B. Now, if the machine has already decided to stay in C, by processing the 0, it will go to the state D. Okay? So, if you look at the computation, you will find things. It is completely weird. Okay? Or you can say the computation is not following computation is not following a straight line. Rather, it is following a tree form, right? Rather, it is following a tree form. Now, the question is, there are various points if we analyze all the branch. Let's analyze this branch. Let us analyze this branch first. If we analyze this branch, that means if the computation done by the machine like this, then the machine will crash, right? And if the machine will crash, it should not accept the string, right? Because machine is not able to process. So one rule: if machine crash, if the machine crashes, then basically it is not accepting. Okay, so machine is not accepting the input. Fine. So if the machine is going in this direction, then it will crash and it will not accept. Okay. But that is not the end of the story. We cannot say the machine will reject this string, because there is another branch for computation, and if you think about, we can go here and then we go in this direction, right? So if we follow this direction, then also we find there is a crash, right? And if there is a crash, the machine will not accept. But still, this is not the end of the story, because we can go here, we can go here, here, and then we can go in this direction, right? Now, if what we are actually doing, we started with the start state, and then if we are following some branch, and what is the last state? Last state is D. After processing all the symbols, what is the last state? Last state is D. So if there exists any single branch in computational tree, this tree is basically called computational tree. So if there exists any single branch in computational tree which starts from start state and goes to final state, then accept. Okay, so if in the computational tree, if we find there is a branch which is starting with the start state, what is the start state? A, and after processing entire symbol, if there is it go in the final state, that is D, then we say we must accept. But if there is no such branch exist, we need to check out all single branch, right? If we check out this branch, what is the final state? B. B is non-final. If we check out this branch, what is the final state? It is A. A is also a non-final state, right? So there are a lot of branch which are not accepting, right? But if there exists one single branch is enough for saying that the machine will accept. Okay? If there is no such branch exist, we need to check all the branch, and if no such branch is existing, which is going from start state to final state by processing all the symbols, then we should reject it. So let's summarize it. In NFA, there exists no branch which goes with the start from start state and goes to final state by processing all symbols from input, then and only then the machine rejects that input. Okay, so if there exists no branch which is going from start state to final state by processing all symbols from the input, if this condition is valid, then and only then we should reject. If there exists one single branch which is going from the start state to the final state by processing all the symbols, then we say the machine should accept it, right? Then the machine will accept the input, right? So this is what the NFA is. The computation, if you look at the computation for NFA is not like a straight line, rather it is like a tree called computational tree, right? So that is the theory about the NFA. Yes, which one is powerful, whether the NFA is powerful or whether the DFA is powerful, is like a debate. We